Hello everyone, welcome to my video on higher derivatives. So we have already seen the notation for the first derivative. We have f prime of x, we have y prime, or we have in Leibniz notation dy over dx. There's more notations that we could use, but these are the main three that I'll be using. The second derivative, so essentially to get the second derivative, this is the notation that we're going to have to get accustomed to. But what we mean by taking the second derivative is you're given a function, you take the derivative once, you get a new function, and then you just take the derivative again. So essentially we're just taking the derivative multiple times. Okay, so for the second derivative, we have f double prime of x, y double prime, or d2y over dx squared. So if you're using Leibniz notation, be careful. Students often get confused because you have to distinguish this between dy over dx squared. This is not the same. So d2y over dx squared is saying take the derivative twice, whereas dy over dx, all that squared, is saying take the first derivative. Once you get the first derivative, you multiply it by itself, you square it. Okay, so this is not the same thing. So you just have to be careful between talking about the exponent and the second derivative. Okay, so be careful for that. Third derivative, we have f triple prime of x, y triple prime, or d3y over dx cubed, similar to the second derivative. So we just essentially put the number of derivatives here. And then lastly, if we jump all the way down here, we get the nth derivative of any number n. The way we write it in this notation is f to the, it's not an exponent, it's a number that's in brackets. So this signifies take the nth derivative with respect to x. Over here for y, we write y to the n in brackets signifying the nth derivative. And then lastly, using Leibniz notation, it's dny divided by dx to the n. Okay, so let's take a look at these examples over here. So the first example for A, we're asked to find the second derivative, f double prime of x, given f of x is equal to 5x squared minus 3x plus 11. Okay. So let's go ahead and do the first derivative. This is simple. We're using power rule on each term, giving us 10x minus 3, and the derivative of a constant is 0, so we get the 10x minus 3. And now that was our first derivative. Now we're looking for the second derivative, so we just, at this point here, take the derivative again, giving us f double prime of x, and the derivative of 10x is 10, the derivative of negative 3 is 0, leaving us with the second derivative being 10. Okay. Let's look at this example here, B, f of x equals x times e to the x. Let's go ahead and find the first derivative. Okay. So if you're getting e to the x as an answer, that's wrong. Be very careful. You have to catch that we're multiplying here. So what do we have to apply? Product rule. So let's go ahead and apply product rule. So just a quick reminder. When you're multiplying two functions and you're taking the derivative, it's the derivative of the first times the second plus the derivative of the second times the first. Okay. So the first function is x, the second function is e to the x, the derivative of x is 1. We leave e to the x, we get a plus. Now we leave the first function, x, and you take the derivative of the second function. Taking the derivative of e to the x remains e to the x. So we have this. And what I like to do is, at this stage here, you can take the derivative of this individually, but what I would do is I would package this up. Both terms have an e to the x, so I'd factor that out. You don't have to do it this way, this is just the way I see it. And we're left with 1 plus x. So now when I'm taking the derivative, instead of taking the derivative of these two terms, I'm just going to take the derivative of this, the simplified version. Okay, so let's go for the second derivative. So here once more we have a multiplication, so we have to apply product rule again. So the first function is e to the x, the second function is 1 plus x. Let's go and do that. The derivative of e to the x is e to the x, it stays the same. We leave the second function, so we get 1 plus x. Plus, because it's product rule, we're still following this rule. The derivative of the second function, so the derivative of 1 plus x is just 1, because the derivative of 1 is 0, the derivative of x is just 1 times, and then the second function we leave e to the x. Okay, so at this stage here, we can leave our answer. The derivative is correct. If it says to simplify, here we could factor out an e to the x. leaving us with 1 plus x plus 1. And this could be written as e to the x, square brackets, 1 plus 1 is 2, so x plus 2. And this is the final answer. Okay, so in this example here, we have f of x equals ln of x plus 4. Let's go ahead and find the second derivative. Again, as always, feel free to pause the video, try the questions on your own, and then compare your answers to mine. So here what we have is ln of x plus 4, which is a composition of functions, so we're using chain rule. We know that the derivative of ln of x is 1 over x. So we're going to, for the first derivative, what we get is 1 over x plus 4. So instead of 1 over x, it's 1 over whatever's in the bracket of the ln. And then we're going to complete the chain rule by taking the derivative of x plus 4, which is just 1. Okay. So this is 1 over x plus 4. And now we're going to take the second derivative. Okay. And there's two ways of doing this. So one, catching that we have a fraction. So we can use quotient rule, which is the way I'm going to do it. But the other way is, and I think the more convenient way of doing it, I think the more efficient way of doing it is bringing this whole thing up. So instead of thinking of it as 1 over x plus 4, we could think of it as x plus 4 to the negative 1. And applying chain rule here. I'd rather go with chain rule, but if you rather use quotient rule, that's fine. Both answers, or both methods, are fine. So let's do it using the quotient rule, because we have the fraction here. So just remember, for quotient rule, if we have a division of functions, it's the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. So what we get is the derivative of the top, the derivative of 1 is 0, times the bottom, which is x plus 4, minus the derivative of the bottom, which is 1, times the top, over the bottom squared. Okay. So 0 times this is 0. Then we have negative 1 times 1, so we get negative 1 over x plus 4 squared. And that's the answer. Okay. Maybe just quickly, let's go ahead and do it using chain rule. So had you taken the second derivative from this stage using chain rule, let me just quickly do that here on top. If you're taking the derivative here, so f double prime of x, what we're going to do is start with the outermost function. We're going to take the negative 1 and drop it, so the negative 1 comes in front. We rewrite what's in the bracket, x plus 4, and then we subtract the exponent by 1. So negative 1 minus 1 is negative 2. And then we multiply, because we're doing chain rule, we're multiplying by the derivative of the inside. So the derivative of x plus 4 is just 1. So this gives negative 1 x plus 4 to the negative 2 times 1. Since we have a negative exponent here, we could just drop it down, giving us negative 1 over x plus 4 to the positive 2. And you can see that these answers are in fact equivalent. Okay, so both ways are fine, doesn't matter which way you do it. Let's go ahead and do D. So we have a square root. This is a common trap, so be very careful for it. The first thing I'm going to do is switch the square root to exponent 1/2. That's always my game plan. And now I'm going to take the derivative of this function here. So the first derivative, we're going to drop the 1/2 in the front, leave the inside, subtract 1 in the exponent, giving us negative 1/2. And this is the trap that students often fall for, so be very careful. We have to take the derivative of the inside. This is often forgotten, so we're applying chain rule because it's a composition of functions. So we have to multiply by the derivative of 1 minus x. So what comes out here is a negative 1. Because the derivative of 1 is 0, the derivative of negative x is just negative 1, giving us that term. Okay. So we could rewrite this as, again, going back to this issue up here, you could leave it in this form, which is the way I would do it, or you could write it as a fraction again and use quotient rule. My advice is to try to avoid using quotient rule, but it's really up to you. Both ways are fine. So I'm going to rewrite this as negative a half 1 minus x to the negative a half. Okay. And now I'm going to apply chain rule again at this stage for the second derivative. So that's going to give me, we're going to drop the negative a half. So negative a half times negative a half is positive a quarter. We're going to rewrite what's in the bracket, 1 minus x. And then we're going to subtract the exponent by 1. We're using power rule. So negative a half minus 1 is negative 3 halves. And then we're going to multiply by the derivative of what's inside, giving us, again, negative 1. Okay. And now we're just going to simplify this. So negative 1 on top. On the bottom, we have 4. This term here has a negative exponent. We drop it down, giving us 1 minus x to the 3 halves. And this is the second derivative. Okay, so in this example here, it's asking us to find f to the 3 of x, so the third derivative. We could also write triple prime. Both notations are fine. So we're given the function f of x equals 4x squared minus 2x plus 3. Let's go ahead and take the derivative 3 times. So the first derivative, what we get is, we're going to drop the 2, 8x minus 2. The derivative of 3 is 0, so we don't write anything else. Let's take the second derivative. Derivative of 8x is 8. The derivative of negative 2 is 0. So we're just left with 8. And if we take the derivative once more, the third derivative, the derivative of 8 is 0. And that's the final answer. So a nice little observation to make here is the fact that if you're given a polynomial, so essentially it's a function whose exponent has positive integers. If the number of the derivative, let's say the third derivative, so here, this value here would be 3. If this value exceeds the highest exponent, then the answer is always going to be 0. That's a nice little observation to make. Okay. So if I had, I don't know, let's take the 50th derivative. And this function here is x to the 4x to the 49, hypothetically. We don't have to take the derivative 50 times. We know that this value here exceeds the highest exponent. So the answer would be, in fact, 0. So in this example here, it's asking us to find f to the 3 of 1. So this is telling us to take the third derivative, and then instead of having a function x, we're going to replace the value 1 into our function, and we're going to get an actual numerical value. Okay, so let's go ahead and do that. The function that's given is equal to 1 over the square root of x. So let's go take the first derivative. What I would do first is get rid of the root, rewriting it as a fraction in the exponent. So we have 1 over x to the 1/2. And on top of it, what I'm going to do is rewrite it as x to the negative 1/2. I think this is more simple. If not, you would have to use quotient rule. So let's go ahead and take the first derivative. So the first derivative here, it's essentially just power rule. So negative 1/2 x subtract 1, negative 3 halves. And I'm going to leave it in this form, and I'm going to take the second derivative. I think this is a lot easier and quicker than using quotient rule 3 times. And now we use power rule again. We drop the exponent, so we get negative 3 halves times 1/2 times negative 1/2 is positive 3/4. X subtract by 1, we get negative 5 halves. Next, we take the derivative once more because we want the third derivative. And now we multiply 3/4 times negative 5 over 2. We get negative 15 over 8, x to the negative 7 halves. Okay. So this is the function. If it asks us to find the third derivative, we're done. But here it's asking us to evaluate it at 1. So what we're going to do is substitute the x by 1. So we could rewrite this as negative 15 over 8 x to the 7 over 2. And at this stage here, we're just going to substitute the x with 1. 1 to the 7 over 2 is just 1, leaving us with negative 5 over 8. And this is the final answer. So why are higher derivatives of interest to us? Well, in our everyday life, we don't use terms like the first derivative, second derivative, third derivative. We use words that we see in physics, such as displacement or your position, velocity, your speed, and acceleration. Okay, so in physics, displacement, which we'll denote as s of t, is the shortest distance between two positions and has a direction. So displacement, so you move from point A to point B, that's your displacement. Velocity, v of t, is the speed and direction of an object, or we could also call it the rate of change of displacement with respect to time. So it's important that in math we're using this term rate of change. It's the rate at which we're changing. So essentially, how fast did you go from point A to point B? That's our velocity. And then lastly, we have acceleration, a of t, which is the instantaneous rate of change of the velocity with respect to time. So what we're saying here is that essentially if you're looking for the acceleration, a of t, that's equal to the derivative of the velocity, which is also equal to the second derivative of your displacement. Okay, so if you're given a displacement function or a position function, then to find the velocity, what you have to do is essentially just take the derivative with respect to time. So if you take the first derivative of the position function, it gives us velocity. And if you take the derivative of your speed, your velocity, you get acceleration. So the second derivative with respect to with respect to time of the position is acceleration. We could take the derivative once more, the third derivative, and that would give us something called jerk. But for now, we'll stop at acceleration. So in this example here, a particle moves through space according to the following function: s of t equals 4t cubed minus 9t squared plus 2t plus 2. So we're given the position function of this particle, and it's asking us to find the velocity, find velocity at time t, find the velocity after 2 seconds, find the acceleration, and then find the acceleration after 2 seconds. So let's go ahead and do this. Just a reminder, the derivative of the position function is velocity, and the derivative of the velocity is acceleration. So let's go ahead and find v of t using that information. So to find the velocity, what we're going to do is take the derivative of the position function with respect to t. So s prime of t is equal to your velocity. So the derivative of 4t cubed is 12t squared minus 9t squared. We take the derivative, power rule, we drop the 2, giving us negative 18t, and then plus 2. Okay. So this is our velocity function. And now it's asking to find the velocity after 2 seconds. So what it's asking for is what's v of 2. So replace the time t with 2, and that gives us 12 times 2 squared minus 18 times 2 plus 2. This is 12 times 4 minus 18 times 2, which is 36, plus 2. 12 times 4 is 48, minus 36 plus 2. 48 minus 36 is 12, plus 2, giving us 14 seconds. So, oh sorry, not seconds. This is the velocity. So the units would be meters per second. Okay. Let's assume it's in meters. Now we have to find the acceleration. So the acceleration we know is the derivative of velocity. So once we have velocity, let's go ahead and take the derivative, giving us v prime of t equals a of t. So taking the derivative of this function here now, so the derivative of 12t squared is 24t, because we dropped the 2, and then minus 18. This is the acceleration function. And yeah. So what's the acceleration after 2 seconds? We're going to just replace 2 in our function. So 24 times 2 minus 18, giving us 24 times 2 is 48, minus 18, it gives us 30 meters per second squared. And that's the acceleration.